What we're going to do in this video is we're going to add an extra fourth coil resonance. Right now that fourth coil resonance is sitting in space off to the side of the 1, 2, 3 system that we normally have hooked to the system. What we're going to do is we're going to put that extra coil on top of 1-2 extraction of the 2.4 Henry coil. These are both approximately 2.4 Henry coils. When we do this, it improves the three-phase balance, and it enables us to make a more conclusive perception regarding whether the time is overclocked or not. The problem that comes in that when we show time reference points of over 180 degree angles, that when we go to try to add everything up to 360 degrees, we don't have a number to assign for that one that's over 180 degree phase angle. So what we're doing is we're bringing the fourth coil in and picking up energy through the air from the first coil in the set, and when we do this, it will reduce the excess 180 phase angle down to under 180 degree phases, phase angle, and then we can add all three of these phase angles up in time by the law of cosines, which we've gone over. And we got all the numbers to do that, and we got everything to show that indeed going around that time circle we've got more than 360 degrees. So having gone through that, going back to our notes here, when I did this I found that former phase angle that was over 180 was shrunk down to 148.4, and the other two phase angles were near 120 degrees, but that it added to 395 degrees, almost 36 degrees over 360 degrees, or 10% extra time. The interphasal loads have not loaded down their source as to actually change its phase angle of delivery from the source. This can happen. Hence both examples are identical phase angles. We're only going to show the output on this video, and we're not going to go to the unloaded state yet, but I've already done that with the unloaded state and found out that it also exhibits 395 degrees, a total difference in phase angles. So then we figure here that let us propose that after 10% of the 465 Hertz cycles per second, can't read it, occurs, one extra magnetic rotation of the advanced phase rotation has occurred. So we're getting 10 extra per second. What this means then is that the line voltage itself has governed a magnetic rotation of 46.5 cycles during this time period, but the extra influence has accomplished 47.5 magnetic revolutions. What this means is that in the time period of sampling one frequency from one source being slightly higher in frequency than that of the line connections, both of these forces added in a vector addition manner will show that this interference effect created by advancing the phase rotation ahead of its source, in fact, during half of the extra rotation brought on by the interference pattern, the extra air core forces may oppose the line delivery one, and in the remaining time period it may aid it. Thus, this becomes the reason for observing cyclic voltages in time on the measurements itself, and essentially why the system itself is not designed or even predicted to reach equilibrium of a steady state value. Luckily, however, in the study of the enhanced phase angles by voltage meter means, the interference frequency of repetition of the extra voltage source is very slow compared to the meter's sampling rate. So what we're going to go do now is just go ahead and turn the device on and go look at our input parameters. And we'll get up here before we waste too much more time. we got the neon on. It's misbehaving today for some reason. When we put weights on that plate, back out again. When we put weights on that plate, it disturbs the resonance just like the cat did. So let's take that stuff off of there and see if it helps the neon a bit. We got a gallon of water behind there. Well, we don't know if that helped any, but let's get back to what we were doing. There's our neon. Seems to be a little more steady now. And we're going up here. We're looking at these 6 meters. And we're noticing that 24.7 is greater than 10.8 plus 13.3 or whatever that is on one internal voltage rise 1 and internal voltage rise on phase 3. Now, we have this extra coil here. Let's see that meter. Right now, sitting in space just that far apart, it's deriving 10.8 volts. Now it's only consuming 1.2 milliamps. And now, interphasal 1-2 has 11.3 volts on it, around in there, and it's consuming 9. It's fluctuating widely because of the neon again. It's going up and down, but we can see that it has 11 point some volts there. Now we're going to put that extra coil on there. At the same time we put that extra coil on there, let's observe the amperage going in to what we're calling phase 1. Okay, that's decreased that to 3.3 milliamps. I think we can see that. Our input voltage went up to 20 volts, and we didn't get to show it. But what this has done, before our three-phase line deliveries were pretty much imbalanced, but now they're much more balanced. We got 0.25, 0.19 and 0.21 amps going into the delivery lines. Now let's look at the 6 meters. From this 6 meters and the law of cosines, you should be able to deduce that there are 395 degrees of phase angle difference all around the circle. You see that the 25.4 volts, that voltage appears to have gone up, is now greater than the sum, or less than the sum of 12.4 and 14, and all the 3 interphasal voltage meters, 1-2, 1-3, 2-3, are all less than the sum of their vector components. But nevertheless, when we do the law of cosines and go around the circle, you will find that it is close to 395 degrees. We'll call that quits. Here's the amperages on our other 2 sources.